When it comes to optimizing GPU performance, profiling and tracing are two essential tools that can help developers gain insights into how their applications are utilizing the GPU device. Rockium provides two powerful tools for profiling and tracing, Rock Profiler and roctracer. Rockium Profiler or Tracer is a tool that helps developers identify performance bottlenecks in their GPU applications. By profiling the application and analyzing its performance, developers can identify the parts of the code that are slowing down the application and optimize them for better performance. There are two modes of Rockium Profiler Tracer: application tracing and GPU profiling. The application tracing mode is used for performance measurement of the application, while the GPU profiling mode can provide us more insights with measurements from hardware performance counters. In the application tracing mode, Rockium Profiler Tracer measures the performance of the application by tracing its execution and measuring the time taken by each function or section of the code. This helps developers identify the parts of the code that are taking the most time and optimize them for better performance. In the GPU profiling mode, Rockium Profiler or Tracer measures the performance of the GPU itself by collecting performance counter data. This data includes metrics such as memory usage, instruction throughput, and shader occupancy, which can help developers identify performance bottlenecks and optimize their applications accordingly. Now let's focus on the measurement of the application's performance in application tracing mode. To perform application tracing, there are various options available for us. As shown on the right side of the slide, the system structure comprises hardware at the bottom, an operating system such as AMD KFD driver in the middle, and interface such as HSA and HIP runtime at the top. Based on this diagram, we can perform application tracing at different levels. For instance, if we use the heap trace option, we will trace the user space level where the heap runtime is located. Using the HSA trace option, we'll trace the level where HSA runtime is located. On the other hand, the KFD trace option allows us to trace the AMD KFD driver level. In general, tracing at a higher level allows users to easily associate the tracing results with the source code and identify the source of the problem issue, but tracing at a lower level provides more detailed information. To perform application tracing with the Rockium Profiler, we can use the command rocprof with the option heap trace followed by the application binary we want to trace. When executed, this command generates 4 output files containing information about the application's execution. In the example shown, we are tracing a vector addition program. Let's take a look at the output files that the command generates. In the results.copy_stats.csv file, we get the time measurement on heap runtime calls. The file is stored in the comma-separated values, that is CSV format. If we convert the file into a more readable table as shown below, we can see that the files aggregate the execution time of memory copy device to host and memory copy host to device. The underlying program calls the host to device memory copy twice and the device to host memory copy twice. This table shows the average duration and total duration of memory copies on each direction in nanoseconds. In addition, we can view the percentage of specific API calls in the overall application execution using the heap trace feature. We can also use third-party software such as Chrome tracing to visualize the performance of the application, which we will be discussing in a while. The results.heap_stats.csv file aggregates the execution time by APIs. We have converted the CSV output file to a table format to provide a clearer view of the data. You should be familiar with most of the API calls other than 3 of them, including the heap launch kernel, heap push call configuration, and heap pop call configuration. These 3 functions are the actual API calls that's behind the triple angle bracket syntax. Every time we launch a kernel, heap will push the call configuration, which includes the kernel dimensions, stream, local memory size, and kernel arguments to the GPU side using the heap push call configuration API. Then the heap launch kernel triggers the execution of the kernel. Finally, heap pop call configuration removes the kernel-related information so the next kernel can start with a fresh status. From this file, we can see that the heap mem copy takes more than 99% of the execution time, so it should be global performance bottleneck. However, you should be a bit careful here, as the percentage is only relative to the total heap runtime call execution time. The kernel time is not counted in this table. The heap launch kernel call is only the process required to kickstart the kernel, but not the kernel execution time. To see the kernel execution time, we need another file. There is another file named results.stats.csv file. Note that this is not the previous file, as the previous file is named results.heap_stats.csv. The results.stats.csv file aggregates the kernel execution time. In our example, the vector add kernel is being invoked once and it takes 283 microseconds to execute it. Finally, other than the aggregated data, we want a version of the data that is not aggregated. In this case, we have the results.json file. It is somewhat readable by human, but visualizing the trace would make it easier for users to understand the executions. To this end, the results.json file follows a standard tracing format so that we can use the Chrome tracing tool to visualize the execution trace. At first, we go to our Chrome browser and type chrome://tracing and upload our JSON file there, and then we can see the visualization of the tracing. As shown on the top of the browser window, the API calls and the kernel calls are shown in a Gantt chart format. We can clearly see that the kernel execution is short and the first memory copy took a great portion of the execution time. The application tracing mode allows us to examine performance bottlenecks at the runtime API and the kernel level. It is usually a good starting point when analyzing performance issues and see if an API call or a kernel is taking an unexpected amount of time. However, once we have identified that a kernel is problematic, the tracing mode provides limited information about the internals of the kernel. In this case, we need to use the profiling mode to examine at a lower level of details that are closer to the GPU hardware. Before we can use the profiler, we need to check what performance counters are available to be used by users. Performance counters are hardware registers that can automatically collect data while the programmers run on the GPUs. The possible collection of program counters are defined by the GPU hardware. Therefore, different GPUs may have different performance counters. We need to run a program to check what program counters are available. Here we run the rocprof least basic command to find the available performance counters. ROCm Profiler provides two types of metrics for profiling code performance, basic and derived. The basic metrics are hardware counters that directly measure the activity of the hardware components such as the compute unit, cache, and so on. Some of the basic metrics provided by ROCm Profiler will be discussed in a while. In the provided screenshot, we can see a part of the list of hardware counters. In addition to basic metrics, ROCm Profiler also supports derived metrics, which are more high-level performance metrics that can be calculated from the basic hardware counters. Derived metrics prints the metrics expressions. These expressions are used to calculate those metrics the command rocprof least derived provides with such information. On the right side of the slide, we can see the various hardware components such as compute unit, L1 and L2 cache, which have subcomponents like schedule, SQ, SIMD termed as SP, vector memory unit termed as TA, L1 cache termed as TCP, and L2 cache termed as TCC. These subcomponents are abbreviated by their respective short forms and the counters are named after these abbreviations. The slide shows some of the hardware counters including SQ_waves, which displays the number of wavefronts, and SQ_inst_value, which measures the number of SIMD instructions executed. The TCC_hit counter represents the L2 cache hit count. TCC_EA_WRREC is the counter for the number of the write requests from the L2 cache to DRAM. It's important to note that the slide only displays a subset of the available hardware counters. Here are some examples of the derived metrics. The value utilization matrix is the percentage of overall ALU utilization. A lower number indicates that the program is not very efficient. This can be a result of a high thread divergence or a highly memory intensive kernel. Value range of 100% is ideal but is very difficult to achieve. The fetch underscore size and write size metric is the total kilobyte fetched from or written to the GPU DRAM. This is measured with all extra fetches and any cache or memory effects taken into account. When combined with the kernel execution time, this number can be used to estimate the DRAM bandwidth utilization. Finally, L2 cache hit is the percentage of fetch, write, atomic, and other instructions that hit the data in L2 cache. GPU profiling. When conducting GPU profiling, we need to provide an additional input file that specifies the metrics to be profiled for the GPU, along with the application binary. GPU profiling requires us to specify the input files. In the example shown in the slide, the input file contains the metrics to be profiled. For example, the first line specifies the performance counters PMC that we want to use. The range field suggests that we care about the first 6 kernels. We also want to profile these metrics on GPU 0 and 1 as our system has 2 GPUs and the kernel function. Finally, we specify the kernel that we want to profile by the kernel name. This is just an example, and we can specify different metrics and GPU configurations in the input file. Now let's take a closer look at how GPU profiling works. To perform GPU profiling, we can use the command rocprof I input.txt o output.csv vecadd, where input.txt is the text file containing the list of metrics we want to profile. Output.csv is the name of the output file, and vecadd is the binary file we want to profile. This command generates an output file in the CSV format. Earlier, we discussed the format of the input file, which specifies the metrics to be profiled for the GPU and the kernel function. Once the input file is ready, we can run the command to start profiling the application. Upon execution, the output.csv file is created, which contains the profiling results. The output.csv file provides us with the necessary data. However, it is easier to comprehend the data in the form of a table. In the output.csv file generated after running the rocprof command, we can find important information such as kernel name, GPU ID, queue ID, queue index, and thread ID. The kernel name represents the name of the kernel that was dispatched, while GPU ID indicates the GPU that the kernel was submitted to. A few metrics are provided even though we did not specify. These metrics are related to the kernel's characteristics such as GRD, which stands for the kernel's grid size, WGR, which is the workgroup size, IDS for the kernel's LDS memory size, SCR for the scratch memory size, VGPR and SGPR for the kernel's VGPR and SGPR number, respectively. Additionally, F bar indicates the kernel's barriers limitations. The SIG is related to the HSA specification and typically do not require users' attention. Following these a few metrics, we can see the metrics we collected. For example, we can see the GPU is busy 100% of the time while the kernel is executing. There are 1.5 million wavefronts that are executed, 6 GB data is written to the DRAM, and 12.5 GB is read from the DRAM. As you can probably see, the profiling mode provides the users with extremely low-level information. With these metric values, developers can understand how their program behaves. For example, developers can check if the kernel is loading an excessive amount of data from the DRAM, is the L2 cache miss rate excessively high, or is the ALU is not being efficiently utilized. Properly using the profiler can identify the problem of the program and guide us to improve the performance. Our next video will discuss Hipify, a powerful tool that can automatically convert CUDA code to HIP code, enabling developers to write code that can run on both NVIDIA and AMD GPUs.